Hi everyone, welcome to this presentation. In this video we are going to see how to implement a switch capacitor converter based electronic transformer. So in this video we will see first an introduction, then the implementation of the electronic transformer. We will show how to derive a model for the electronic transformer. We will show how to do a design example, and then we will test this example using LTspice simulations. This video is the video number 8 in this series about switch capacitor converters. The series started with this video, Power Electronics number 17, and the next videos up to Power Electronics number 23 are related to switch capacitor converters. So please, if you are interested in this topic, take a look at these previous videos. Up to now, we have seen many topics, many things related to switch capacitor converters in the previous videos. So right now we are in a good situation to see other more sophisticated applications of switch capacitor converters. So what we are going to see here is how to develop the equivalent of a magnetic transformer, a magnetic voltage transformer, as this one that we are showing here. We know very well how a transformer works. We have an input voltage V1 and output voltage V2, which is going to be equal to the ratio of the turns in the primary and the secondary, as shown in this expression here. And of course, because ideally the output power and the input power are going to be exactly the same, then the current circulating here at the output is going to be this ratio N1 over N2 times I1. We know this very well. So the idea now is how to develop an electronic transformer based on switch capacitor converters. So in our case, we are only using bidirectional switches and capacitors, and we are not including any, in principle, in the main converter. We are not going to include any magnetic device to do the transformation. So we know that using switch capacitor converters and including a number of capacitors, for example here N, then we can implement converters with a given ratio between the input and the output. In the case of N capacitors, we have seen that we can have this ratio 1 over N plus 1. So the output voltage is going to follow this expression here, N plus 1 times the input voltage, and the output current is going to be like this, 1 over N plus 1 times I1. The development of electronic transformers is very popular nowadays, so we're going to see how to do this using the switch capacitor converter technology that we have seen. We're going to take as an example the generic step-up-down switch capacitor converter that we have studied in this previous video, Power Electronics number 22, with this topology here. So we know that with this converter we can get an output voltage that is going to be N plus 1 times the input voltage. And also we have seen that this converter is bidirectional, so we can connect here the voltage source, if we like, on this side of the converter, and then connect on this other side the filter capacitor and the load, and then we will have here on the other side a voltage that will be 1 over N plus 1 the input voltage. So we have seen this. We have also studied the operation of the converter quite in detail. So we saw that during interval phi 1 we have this equivalent circuit, during interval phi 2 we have this other equivalent circuit, and then by studying the transfer of the charge between the different states, then we can analyze the converter and get the different characteristics of the converter. Now we have to see that when we studied these converters, we didn't make any assumption about the input voltage. Just we have an input voltage here, we are going to get this ratio here. So this voltage can even have any value or can even be negative in the other direction, because at the end the only things that matter is that charge that is going from one structure to the other structure. So we can see that if we change here the polarity of the input voltage, then automatically we are going to have the reverse polarity here at the output. We can see this very quickly in a simulation. Here we have the circuit that we have tested previously in this previous video. So here we have input voltage equal to 12 volts, and we want to generate around 48 volts here at the output. So we can run the simulation and look at the output voltage, so we can see how it is going to increase, reaching the final value, which is something like 45.1 volts, because we know that we have an output series resistance in these converters. We have studied that. But here the point is that if we change this voltage here, say that we place here minus 12 volts, and we run the simulation again, automatically we can see how the output voltage reverses and gets the same final value, but with a negative polarity. This is because our converter is bidirectional, so it can operate with negative input voltage, positive input voltage, and so on. So this behavior automatically sparks the idea of making AC-AC converter with this type of switch capacitor converters. So we are going to investigate this further in this presentation. So coming back to our topology, we can understand then our converter, step up down switch capacitor converter, as having a first port here on this side that we can consider the primary of our transformer, and then another port here on the right side that we can consider as the secondary of our transformer. The output voltage V2 is going to be approximately n plus 1 times the input voltage, and also the input voltage can be approximately 1 over n plus 1 times the output voltage, the voltage V2. So with this we have a transformer with a voltage ratio which is equal to n plus 1. And can operate bidirectionally. However, we have an important drawback in this converter, which is that we don't have isolation as in a regular transformer. So this terminal here at the input is connected with this other terminal at the output, the secondary. So there is no isolation in this type of converters. Here we are showing the equivalent circuits and the different characteristics that we have seen in previous video when we studied this converter. Here we see the equivalent circuit with the voltage ratio n plus 1, the equivalent resistance N over Fc, where F is the switching frequency, C is the switch capacitance, and N is the number of capacitors in the converter. And here is the same circuit when the converter is operating in step down mode. So we can see how the equivalent resistance is here, the output resistance of the equivalent circuit are also in the ratio of n plus 1 squared, which is n plus 1 is the ratio of the input voltage and the output voltage. So this is also important to note, because we will see that this is interesting when modeling the whole transformer. And here we have the other characteristic, how to obtain the output voltage ripple, the efficiency, and also the dynamics of the converter, both in step up mode and in step down mode. In step down mode, remember that we have two peaks for the voltage because we have two injections, or do different injections of charge into the output capacitance, and we have these values also of the efficiency and the dynamics and so on. This is what we are going to use for the design of our converter. Now we have to note also that in a switch capacitor converter like this one here, the current that is going to circulate here through the input is going to be a high frequency current. So we are going to need some kind of filtering at the input. For example, if we run here the simulation, we can check, for example, the output voltage, that is okay. We can add another pane and see the current that is circulating here. So we can see that this current is formed by different peaks due to the charging of the different capacitors. So we need to implement an EMI filter at the input. But also we want that our circuit to be bidirectional, totally bidirectional, so we need to implement filters at the input and also at the output. This is in both terminals, in both ports of the converter. So our final converter is going to look like this. We add an input inductor here, L1, to do the filtering, and another inductor here, L2, at the secondary, also to do the filtering, so we can use at any time each of the ports. Here we select the values of the switching frequency, F, and the switch capacitance, C, and we don't have to do anything else. This is going to operate like a real voltage transformer. We can apply voltage at the primary and the load at the secondary, or voltage at the secondary and the load at the primary, and so on. Let's see now the equivalent circuit of our electronic transformer. Here we can see in the circuit, this is an ideal transformer, which is representing the behavior of the switch capacitor itself with a ratio 10⁻⁴ over n plus 1. So 1 in the primary and n plus 1 in the secondary. In series, we have the equivalent resistance N over Fc. We have placed this on the high voltage side, on the secondary side in this case, but we could put this resistance on this other side, transforming the value with the ratio as we do in typical transformer. And this is not a coincidence, because in a switch capacitor converter, because it's a bidirectional converter, the losses have to be the same in one direction and in the other direction. So adding to our ideal transformer, we have of course the input inductor L1 to do the filtering, the input capacitor here CO1, which in reality is the output capacitor, the filtering capacitor when we go or sending energy from the secondary to the primary. Then we have this other capacitor, of course, at the output, CO2, and then the inductor L2. But now we have to add another element here that we have named CX. CX is a capacitance and that we have to place here in order to have the complete behavior of our circuit. And this capacitor can be calculated approximately with this expression here. It will be n times the value of the switch capacitor, C, plus the series equivalent of the capacitance of a capacitance given by C over N with the output capacitance CO2. But of course, we can question here, why do we need to include this capacitance in parallel with the input of our transformer? So let's investigate this a little bit further. When we model the switch capacitor converter using an equivalent transformer, we are considering only the operation of the converter at high frequency, at the switching frequency. But we have also to take into account the effect of the converter at low frequency. So if we take this into account, we can see that during interval phi1, when we close switches phi1, we are at the end applying here in parallel with the input a total capacitance that is equal to n times C. And during interval phi2, what our converter can see from this point is the following, because in this interval phi2 we are closing switches phi2, then it is going to see 3 capacitances, or n capacitances in this case, in series with capacitance CO2. So the equivalent capacitance that it is being seen from this point is this value here. So this is the reason why we have to consider these two capacitances. But now we could say, okay, but this capacitance here is only applied during half of the time, and this other capacitance is again applied only during half of the time. So this could only be taken into account with 1/2 of this value, and the same thing with this. But this is not the case, and we are going to see this in the next slide. What we are interested in here is in the average behavior of a capacitor when it has a switch in series, like here, for example, in this case, if we have a DC voltage, a switch that is commutated at a switching frequency F, and then we have the capacitor C. What is going to happen here? The first time that we close the switch, the capacitor is going to be charged to VI. So if we keep opening and closing the switch, there is nothing that is going to change. We are going to keep the same voltage. So this is the first clue that a capacitor with a switch in series is going to behave like the same capacitor. Let's take a look here now to this other situation in which we are applying any voltage here to our switch in series with our capacitor. If we open and close this switch continuously, then the voltage that we are going to have across the capacitor is going to follow approximately the input voltage in a waveform like this one. If the switching frequency is high enough, the average value of the capacitor here in this circuit is going to be approximately equal to the input voltage. So at the end, the average circuit is equivalent to having the full capacitor all the time. So the current that is going to circulate through this circuit, the average current is going to be the same as the current that is going to circulate through this circuit here. So this is the reason why we need to consider the full value of the capacitances. Let's check this statement very quickly with a simulation. Here we can see the actual circuit with the switch in series with a capacitor. We have added here this LC circuit in order to obtain the average current circulating into the circuit. So we are driving the switch at a frequency Fs, and with a given duty cycle. We have here the parameters 100 kHz and the duty cycle is 0.5, and this would be the actual circuit. What we are stating is that this actual circuit is going to behave like this average circuit here, so it's going to be approximately equal to having this capacitor, the full time. So we are adding also here this averaged circuit in order to see also and compare the current through the capacitor here with the current entering into this circuit here. So now we will run the simulation, and then we can check several things. We can show here the input voltage, which is a sinusoidal waveform at 50 Hz and with an amplitude of 10 volts. And then we have our averaging, our filter circuit. And if we check here the voltage across the capacitor here in this circuit, we can see that the voltage follows perfectly well the input voltage, as we have seen in previous slide. So now we can measure also the current entering in the whole circuit, which could be the current circulating through this inductor here, and then we can see that it corresponds to a capacitive current. So let's compare this current with the current that is circulating in this averaged circuit. So this will be the current through this capacitor here. So we can see that they are pretty much the same. There is a small difference but we can consider this as a good approximation. If we calculate the RMS values, we can see here is 22.2 milliamperes and here is 26.6 milliamperes. So with this we have everything and we can go ahead and do a design example of transformer. In this case we are selecting here a transformer with an input voltage of 60 volts, 50 hertz, power of 100 volt amperes, a voltage ratio 1 to 4, so the output voltage is going to be 240 volts, 50 hertz also. And then the load resistance, the nominal load resistance, is going to be 576 ohms. This is the value of the output current and the value of the input current in this situation. And of course, our transformer can also operate applying voltage at the output, 240 volts, and then it will generate 60 volts at the output, and the nominal load for 100 volt amperes will be 36 ohms. So let's see how to design this transformer. So we want a ratio of 1 to 4, so we have selected a topology with 3 capacitors here and equal to 3. We have also selected the typical values that we have been using in all these previous videos, the value of the switch capacitor equal to 10 microfarads and the switching frequency 100 kilohertz. So with this 1 over Fc is equal to 1 ohm, which is reasonable for this application. And now we are designing the output capacitor and designing the behavior on the step up operation. So here we are going to have 60 volts RMS at the output, 240 volts RMS. So the situation is like shown here of the equivalent circuit. The equivalent resistance is going to be 3 ohms. So this is quite low for this application, so it's okay. And then we have selected a value of this capacitor here on this side of the converter equal to 2 microfarads. Why? Because in this case the peak-to-peak voltage that we are going to have when the current at the output is maximum is going to be 2.96 volts, which is something like 1% of the output voltage, so this seems reasonable. And also, if we take a look at the time constant of our circuit, it is going to be only of 6 microseconds, which is much lower than the period that we have in our converter. The waveform that we are designing is 50 hertz, so the period is 20 milliseconds. So we have dynamics enough for reproducing this frequency. Similarly, for the step-down operation, we have this equivalent circuit. We have selected 10 microfarads for this capacitor here at this point on the primary. Because with this capacitor, in this case, we know that we will have two peaks, ripples, different ripples on the voltage. So the maximum value of the current will be something like 1.77 volts and the other one 0.59 volts. Very much lower than this value here, 60 volts RMS, so this will be okay. And also the time constant is 1.87 microseconds, so it's much lower than 20 milliseconds, so we are good also with this value. And finally, for the EMI filter inductances, we have selected for L110 microhenries, because with this value we are going to have a circuit with a cutoff frequency of 15.9 kilohertz, which is much lower than 100 kilohertz, almost 1 decade below this value. And also for the output inductance, for the inductance on the other side, on the secondary side, L2, we have selected 50 microhenries, which is going to give the same frequency, very much lower than the switching frequency. So summing up, this is our circuit, the actual circuit of our converter with all the values that we have selected. And this is the equivalent circuit and the electronic transformer model with all the different values that can be calculated as we have seen in this presentation. So now what we are going to do is to check the operation of our converter by doing several simulations using LTspice. Here we can see the schematics. On the top we have the full converter with everything, with all the elements that we have just obtained. And here at the bottom we can see the equivalent circuit, the model of our transformer, also to check that it is going to behave as the actual circuit. So now we are applying here at the input on both circuits the input voltage with 60 volts RMS. This is the peak value, 50 Hertz. And then at the output we have the load, the nominal load, 576 ohms. And we want to get here something like 240 volts RMS. So let's run the simulation. This is going to be a transient simulation up to 60 milliseconds. So let's run the simulation and see here, for example, the output voltage and also the input voltage. So we can see in green is the voltage at the output, the secondary voltage, and in blue we have the voltage at the input. So the input voltage is 60 volts RMS, of course, and the output voltage is 238.6 volts, of course, because we know that we have some series resistance in the circuit, so the voltage is a little bit lower. This is similar as in a real magnetic transformer. And now we can take a look maybe at the current through the primary. So let's add another pane here and show the current that is circulating through the primary. So we can see this is a sinusoidal waveform. It is filtered by our inductor and our capacitor together. And if we also look at the input voltage here, we can see in blue the input voltage and in red the input current. So we see how we have capacitive behavior at the input, which is due to the effect of this capacitance here, Cx mainly. We can check in our model the other values. For example, here the voltage, let's see here on this pane, the voltage at the output, so it's the same as the voltage on the actual circuit. We can check also the current here through the input in our equivalent circuit, and we can see how both of them are very similar. Here is the current at the input of the model, and IL1 is the current at the input of the equivalent of the actual converter. Let's see this a little bit better, so we can see how in steady state both waveforms are very similar. Now here we are testing our converter in the other direction. Here we are applying on this side a voltage of 240 volts RMS on the actual circuit and also on the model. And on the other side, on the primary side, we are placing the nominal resistance of 36 ohms and also here. So now we can run the simulation and look at the output or the voltage at the primary side and also the voltage that we are applying on the secondary side. So in blue we can see the voltage of 240 volts, and in green we can see the output voltage, which is something like 59.6 volts, very close to 60 volts RMS, but a little bit lower due to the series resistance. And also we can take a look in another pane here at the input current in the actual converter, and compare it with the input voltage. So we can see in red the input current, in blue the input voltage on this part, on the secondary. So we have the same capacitive behavior. We can compare also the current that is entering on this side with the actual circuit. So we can see also that both currents are very similar. So this is a good model for our transformer. We have seen also that the dynamics of our circuit is very good, so we can think about using our voltage transformer in other applications at higher frequency. For example, here we are applying at the input 60 volts RMS, but at 400 Hertz, as in airplane applications, like this also here in the model. So let's see if our voltage transformer, our converter, can also operate at this frequency. So here we are going to show the output voltage and here the input voltage. So we can see that the output voltage can be reproduced the input voltage without problem at 400 Hz, and probably it could operate even at higher frequencies. We can even add another pane and add, if we like, the input current, the input voltage, showing the capacitive behavior, and then we can compare it with the input current here. So we can see that they are pretty much the same. Note that the zero here of the current is at this level, so this is the current in red, and in blue we have the voltage. Now we are testing our transformer with an inductive load. So we have here an inductive load with 1 Henry here and the same resistance of 576 ohms. And we are applying here at the input the same voltage of 60 volts RMS, and the same situation for the model of our transformer. So let's run the simulation, and then we can see the output voltage. Here we can compare it with the input voltage, which is 60 volts RMS in blue, and in green we have the output voltage applied to our inductive load. So we can check the output voltage RMS value, which is 238.9 volts, which is good. We can take a look also at the current at the output. So we can see that in red is the current and is inductive compared with the output voltage in green. We can also check the output voltage of our equivalent circuit here. So we can see that is exactly the same as in the case of the actual circuit. So the current is going to be also the same, of course. We can check the input current here in our circuit, in the actual circuit, which will be like this in pink. Remember that the zero level is now here at this point, and compare it with the input current into the transformer model. So we can again see that at the steady state they are pretty much the same. Now let's do a simulation with a capacitive load, but now applying the voltage at the secondary side of 240 volts, and then we are connecting on the primary side a capacitive load with a series resistance of 36 ohms and a capacitor of 100 microfarads. Same situation for our equivalent circuit. So let's run the simulation, and then we can see the voltage at the primary now, which is our output voltage now, the voltage at the input, which is this one now in blue, and then we can check the current at the output to the primary, which is shown here in red, and then we can see the different values, the voltage at the primary side is 59.8 volt as expected, and then also the current circulating through the primary, which is now our load, is capacitive with regards to the input voltage. We can take a look at the same waveforms in our model, so we can see the output voltage, which is exactly the same. Of course, the output current is going to be the same. We can check the current entering now through the secondary at this point here. So this will be this waveform in peak, and compare it with the current entering here in the model, and we can see that they are pretty much the same. And finally, a simulation using a nonlinear load. Here we have connected at the secondary a full rectifier with an L filter and a series resistance with the input voltage of 60 volts RMS. The same situation for the model circuit. So this takes a little more to do the simulation. So I have here the results to save time. And we can see the primary voltage here, the primary current in gray, and then here we have the secondary voltage. We can check that the average value is 239 volts. The current circulating through the secondary before the diode bridge. Here is the current circulating through the resistance, and here is the current that goes through one of the rectifying diodes. We can also check that the waveforms in the average circuit are approximately the same. So we can see that our circuit, our transformer, can be applied in many different situations because the dynamics of the transformers is very good. It's in the range of a few microseconds. So as long as we use at the ports of the transformer loads with a dynamic much slower than our transformer, in principle the circuit is going to behave well. Finally, I would like to say that in order to implement this type of circuits, this voltage transformer, we need to use bidirectional switches. So all the switches in our circuit have to be bidirectional, fully bidirectional. We have seen this in this previous video, Power Electronics number 20, how to implement these bidirectional switches. So please, if you are interested in this topic, then take a look at this video. Okay, this is all today in this video. Thank you very much for watching once again. I hope that this topic is interesting for you, and I hope to see you in the next video. Goodbye now.